No. All right. What you need to get good at is the ability to look at a structure of a cyclohexane ring of some kind, drawn from above, and then to draw a chair conformation that is the most stable conformation of that particular molecule. But it's not as easy as you think. It's not a matter of just, oh, I'm just going to make everything equatorial, because you have to get the connectivity and what I'm going to call the stereochemistry correct. So I'm going to draw a molecule. This is not a cyclohexane ring, but you can draw a chair conformation for it. It's a 6-membered ring, and one of the atoms in the ring is an oxygen. And then we're going to just draw some OH groups here and there. All right, so 4 OH groups and then a CH2 OH group. That's called a hydroxymethyl group. The molecule I've drawn, you'll learn later in 352, is called beta-D-galactopyranose, or galactose, if you want to call it that. And I've asked questions before on an exam where I'm like, which of the following is the most stable chair conformation of this molecule? And some of you, or some of your peers from previous years, hear the words most stable and chair and jump to the concept equatorial. Equatorial is more stable than axial. Did you guys talk about that? Yeah, you know why? 1,3 diaxial interactions, steric hindrance. And so that's true, but it's the wrong answer to this question. If you were going to be like, oh, everything needs to be equatorial, you would actually draw the wrong molecule. So here I am going to draw, oh, this is the conformation where everything's equatorial. These are not the same. You can tell that they're not the same because they don't have the right, what I'm going to call stereochemistry. Stereochemistry is related to 3-dimensional shape. And so let's go through each of the OH groups, 1, 2, 3, 4, 5, and 6. Let's go through each of the carbons, just actually 1 through 5, and see whether the drawing on the right matches what we know about the 3-dimensional shape of the molecule. And just to get our perspective right, this is the overhead view, and then on the right we have the sort of from the side view. So if we want to get this overhead view, you sort of have to imagine yourself looking down on this ring from above. Okay, so looking down on this ring from above, the OH group on carbon 1, that's what, up or down? You can tell it's an up because it's a wedge. Okay, over here is the OH group on carbon 1, up or down? So up and down is different from axial equatorial. That's a concept you need to get. Up can be either axial or equatorial depending on what carbon you're on. How do you know this is an up OH group? Which direction's up? Up, right? That's very helpful. From our overhead view, up positions are ones that point towards the hovering eyeball of doom. Or if you want to imagine this as the ring is sort of the equator of a globe, then up is towards the North Pole. Okay? So this OH group is up, so is that one. All right? What about carbon 2? That's down. Is it down here? Did I get mixed up? I got totally mixed up. I started numbering things the wrong way. You guys gonna sit there and take that? Also, I counted 5 twice, inexplicably. Just you were being kind to an old man. Thank you, but you can call me out on that. All right, so carbon 2 is a dash, that's down. Do you recognize that that's also down? Yep. I saw a thumbs up, which confused me. That's down, right? Yes. We're going left, right? Right. Which left? Anyway. So notice that on carbon 2, the down substituent is down equatorial. And in general, substituents on down carbons, that is carbons that are sort of at a valley, they're going to have up equatorial and down axial substituents. And it might help, by the way, when you're first learning about chairs, to draw in the substituents that are implied, the hydrogens that are implied but not shown. Notice on carbon 2 sort of occurs at a peak, and the up substituent is up axial. Okay, so we can go through a little bit more quickly. Carbon 3 is up, and it's up there. So far, the first 3 carbons are totally fine. They've got the right stereochemistry, that is, they've got the right shape, the right up-down relationships. Let's look at carbon 4. In our drawing here, carbon 4 should also be up, but it is not. It is down. Okay? On a significant percentage, I would say 30 to 40% of students have missed that on an exam before, so don't let it happen to you. Again, if all you've done is memorize equatorial is more stable than axial, then you're going to rush through this and do it wrong. This cannot be the most stable chair conformation of this molecule because it is not even the right molecule. Yes? On carbon 2, is that group always going to be down? You've never seen one up? Yes, there are. Well, no, actually. I meant, yes, there are examples where there are OH groups on carbon 2 that are up. There's a biologically important sugar called mannose that has the OH group up on 2. Yep. Others? Okay, so you would rule this out because it is not even the right molecule. Now, just for fun, we'll compare the last carbon, that is an up substituent on carbon 5, and indeed it is up here. These carbons 2 and 5 are somewhat challenging to see whether a group is up or down, axial versus equatorial. It will help you on these carbons to draw in the other substituents. So, what we've drawn here, it turns out, is not even the same molecule. It's what's called a stereoisomer because the connectivity is the same, but the 3D shape of the molecule is different. When I say the connectivity is the same, I mean this oxygen is still attached to 2 carbons. All of the groups are bonded to each other in exactly the same way, but the molecules are different. They don't have the same shape. Turns out the one on the right is called beta-D glucopyranose, and you can tell by the different name that those are different molecules. If we were to draw this in an overhead view, the way you would do this is you would draw the hexagon, you'd put the oxygen somewhere. Really important is to number around the ring in the same direction as you did here. If it goes 1 to 2 to 3 to 4 in sort of a clockwise way, you need to be clockwise here. Otherwise, you'll get the wrong answer. And then you just go carbon by carbon and say, okay, the OH on carbon 1 is up. The OH on carbon 2 is down. The OH on carbon 3 is up. The OH on carbon 4 is down, and the hydroxymethyl group on carbon 5 is up. And you can see the key difference between these two and it all comes down to carbon 4. That's where there's the difference. Okay? So these are examples of a kind of isomer called stereoisomers. Stereoisomers have the same connectivity, meaning all the atoms are bonded to all the same atoms. Atom by atom, everything's bonded to the exact same things, but different 3D shape. And importantly, stereoisomers are not interconvertible by rotation around carbon-carbon bonds. Okay? That's something that's going to come up a little bit. But let's answer the question then, what is the most stable chair conformation for this molecule? How would you alter this structure in order to make it beta D galactopyranose? What would you do? So I'm hearing the word switch. Switch what? Go ahead.
Put carbon 4 on the axial.
Yep, put the OH on carbon 4 at the axial position. So that would be this, pointing straight up. Okay, good. Now, people often have anxiety about OChem. Is that the understatement of the year? Is that your life right now? I also have anxiety about OChem. Not this OChem, but well, I do worry about you guys and teaching you guys, but I also, the whole proposal thing was a major source of anxiety. So the question that some people ask is, when I'm drawing the chair, is there a way that I can always get the right answer first so I don't draw the other chair? And the answer is no. You just have to draw it and then draw the other chair and then compare the two and make the decision. So you don't need to be worried when you start with an overhead view like this and then you draw the chair. You don't need to be worried, what if I draw the wrong chair first? And the answer is, don't worry about it. Just draw the other chair and then you can clearly see the difference between the two of them. For example, the chair that we've drawn here for beta D galactopyranose is indeed the most stable chair. But what if we had started, instead of having that oxygen in the ring at sort of one of the up carbon positions, what if we had started with that one? Going around the ring at carbon 1, and maybe it'll help to number the carbons of the ring. Carbon 1, the OH group would be up. Carbon 2, the OH group would be down. Carbon 3, the OH group would be up. Carbon 4, the OH group would be up. And then carbon 5, the hydroxymethyl group would be up. Okay, so what if you had drawn this first? Go ahead.
Does it matter at which point you put the oxygen during the chair?
Does it matter at which point you put the oxygen? Yes and no. When a chair flips, axial substituents become equatorial, and equatorial substituents become axial, but up substituents stay up and down substituents stay down. Now for the carbons in the ring, you will notice that flipping the chair means that carbon 1 here that was sort of at a valley, I call that a down carbon, is now at a peak. It's an up carbon. So does it matter whether you put, if you're doing a carbohydrate like this, a sugar, glucose or something, does it matter where you put the oxygen? Yes, in the sense that if you put it at an up carbon, you're going to draw one chair, and if you put it at a down carbon, you're going to draw the other chair. But of the 3 up carbons, does it matter which one you chose? No, as long as you go around the ring in the same sense and get everything in the right place. Okay. Now, comparing these two, can you see that the one on the bottom is worse? Why is the one on the bottom worse? More stuff is axial, right? In general, you want to minimize the number of things that are axial and maximize the number of things that are equatorial, whilst keeping all of the up-down relationships the same. Okay, yes?
Could you explain why axial is less stable?
Yeah, why is axial less stable? The best way to do that is maybe through this Spartan app. I'll just show you, let's see, a 6-membered ring. And what should we put on it? T-butyl group, sure, that's fun. Okay, so here is the ring in its chair conformation, and they've drawn the T-butyl group, the tert-butyl group, equatorial. Tert-butyl is huge, as you've learned. It's got an A value. Did you guys talk about A values, sort of quantifying bigness? The A value for a tert-butyl group is 5, or almost 6, which means that having the tert-butyl group axial versus equatorial, it's actually 5 or 6 kcals per mole less stable axial. Why is that? Well, if we draw, in fact, it doesn't even, this is funny, having the tert-butyl group axial is so bad that it doesn't even want to make that chair conformation. So we got to go back to the drawing board. Let's just do a methyl group. All right, so here's with the methyl group equatorial. Here's with the methyl group axial. And the problem with axial is that the axial substituent here, no, it's not going to point, bumps into the other axial substituents that are hydrogen. You can actually see that here. Can you see the methyl group? It's not perfectly axial, it's sort of leaning. Have we talked about leaning and while you were sleeping? No? Okay, there's a great rom-com, Christmas rom-com from the 90s called While You Were Sleeping, Sandra Bullock. And there's this great scene where well, anyway, you have to watch the whole thing, but basically this Joe Fusco, this Chicagoan who's kind of gross, say, hey, Luce, is this guy bothering you? Because it looks like he's leaning and making advances or something like that. Anyway, the methyl group is leaning away. And the reason it's leaning away because it's bumping into those axial substituents. You can see that in the space filling model. We're looking down, there's 2 hydrogens that are pointing towards us, and the methyl group you can see is touching them. So that's called a 1,3 diaxial interaction. It's electron repulsion. Go ahead. Take turns. Follow-up question.
Okay, slight follow-up question, but Nate mentioned that when you do the opposite chair, it like looks opposite, and it's important because it makes it easier to just help me understand why it's easier to do that.
Let's see. I'm not totally sure exactly what he said. These are 2 opposite chairs.
You just drew it differently.
And one way you can, there is a way you can draw it differently. It actually doesn't matter. So some people, when they draw chair flipping, do this. That's okay in the sense that it communicates to yourself that something has changed, but drawing 2 chairs like that and saying there's a change is kind of like, I'm going to get rid of, well, we'll leave the, get rid of the methyl group. When you look at a chair, okay, there it is. That's when it's sort of going this way. If I step to the side and rotate just a little bit, then it looks like it's going that way. So drawing two chairs like this and saying, oh, there's a chair flip and it's obvious, to me it's kind of like, but I just took a step to the left. So like, what's the difference there? The important thing to remember, how you draw the flipped chair actually doesn't matter. If you want to draw it that way to convince yourself that something happened, then that's okay, more power to you. But the thing that happens when the chair flips is up carbons become down carbons become up carbons, axial substituents go equatorial, equatorial substituents go axial, but up substituents on the ring stay up and down substituents stay down. As long as you keep all of those rules, you're going to get it right. So notice that with these two chairs that I've drawn, and we've said that the one on top is more stable because it's got fewer things axial. So we'll draw a big arrow there and a smaller arrow there, equilibrium arrows. Notice that I've drawn the chairs in the exact same orientation, but notice that what used to be at an up position in the ring is now at a down position. If you get that right, you're well on your way. Then notice all of my groups that used to be up in the drawing above are still up in the drawing below, and the group that was down is still down here. So you can, and it wouldn't have changed anything if I had drawn the molecule this way. It's like I literally just took a step to the side and now I'm viewing the molecule from a slightly different perspective. From a teaching point of view, I agree with Nate that it can be helpful to draw the molecule in this slightly different way so that you remember that something happened. I'm really struggling here, but do you see how the two ways that I've drawn this, they're exactly the same molecule in exactly the same shape? I'm just looking at it from one side versus the other. Okay, there was another question. No? Nothing? Okay. All right. Anything else on chairs? Worth practicing? Go ahead.
So just the OH in the bottom left on carbon 4, is that axial or is that?
This one here?
Yeah.
That's an equatorial up. And if you get confused on what's equatorial versus axial, it can help to draw both substituents in, and then it becomes clear. So this hydrogen is down axial, and then the OH on carbon 4 in this chair is up equatorial. One way to tell that it's equatorial groups are always parallel to the bonds that are one carbon away. So from carbon 4, go to carbon 3. This line here is going to be parallel to this line. Okay, others? Yeah.
The up down is basically just according to the view.
Up or down is according to the view, meaning I've chosen to draw the molecule from this perspective, and so up is where I'm looking at the molecule, yeah. Okay, let's talk a little bit more about this concept of stereochemistry. Stereochemistry is cool because you begin to see that there's more to molecules than you originally thought. These two are beta-galactopyranose and beta-glucopyranose. Those are stereoisomers. They don't do the same things in biology, but it's a really subtle difference, right? The only difference is an OH group is up over here, but down over here. That kind of shape thing matters in chemistry and biology. And we're going to talk about how. But in general, you need to know the concept of stereoisomers, which is same connectivity but different shape. Now, I've heard that you talked about this in Chem 105 or 106, I can't remember which, but that you did it really fast and it was confusing, and then there were exam questions on it. Does that basically describe your experience? Okay, good. Well, we're going to go through it a little bit slowly. It will still be confusing, but you're going to get it, and there will still be exam questions on it. So, stereochemistry is interesting because you already have experience with it in the world around you, but you may not realize it. Before we say anything more about that, you need to know that there are two and only two classes of stereoisomers. Stereoisomers is a general term we use for molecules that have the same connectivity but different shape, like glucose and galactose above, but there are only two kinds of stereoisomers. There are stereoisomers that are mirror images, and let me just be clear, stereoisomers have the same connectivity, but they are not the same compound. And I'm not talking about they're drawn differently, but if you flip them over, they're the same compound. I mean, they actually have to be different. So, there are stereoisomers that are mirror images of each other. Those are called enantiomers. And then there are stereoisomers that are not mirror images of each other. And these are called diastereomers. Any kind of stereoisomer that is not an enantiomer is a diastereomer, period. So examples of things that are stereoisomers but are not mirror images of each other. There will be lots of examples of this, but one example that you are already familiar with is the concept of E and Z stereoisomers about double bonds. These have the same connectivity, but you can see they're not the reflection of each other. They're not mirror images of each other. A mirror doesn't change cis to trans or trans to cis. So, because they are not mirror images, we're going to call them diastereomers. In OChem, cis and trans issues are always issues of diastereomers. You maybe have another example of this that you've seen before. Perhaps on Friday, I'm not sure if you talked about this, but let's talk about these two cyclohexanes. In the one on the right, the methyl groups are trans to each other. One is up and the other is down. In the one on the left, the methyl groups are cis to each other. They are both up. These two are not mirror images of each other. So they must be diastereomers. Diastereomers is what we call any stereoisomers that are not mirror images of each other. Okay. So I told you that galactose and glucose are not the same thing. I told you they were stereoisomers of each other. Here is the chair of galactose. Here is the chair of glucose. Are those two mirror images of each other? Nope. So therefore, they must be diastereomers. Okay. Why do we care? One of the huge reasons that we care is that diastereomers always have different chemical and physical properties. They can be isolated from each other. They do different things. Enantiomers, you will see molecules that are mirror images of each other have the same chemical and physical properties, except and there are two exceptions, and only two. The first is how they interact with light. And the second is how they interact with biology. Okay. So that's some classification. Those are some definitions. And we're going to push you on those definitions for sure. And problem set 5 gives you an example of what you can expect, the kinds of questions you can expect. Here are two molecules. What is the relationship between the two molecules? All right. Let's deal with this issue of not the same compound. Okay. I need to reveal to you some of my evil tricks. So this is the part where the evil scientist is monologuing. I won't tell you my Doofenshmirtz backstory about why I am so evil, but I will show you my latest innator, which is concealing molecules that are actually the same thing and trying to deceive you into saying that they're different. Okay? So, classic example. With these, let's just look at this one. I could redraw that molecule like that. And you might be tempted to conclude that they weren't the same thing, but they actually are. So beware, this is the pancake flip innator. Beware the pancake flipinator. If you put your molecular spatula under the molecule on the top and flip it over towards the bottom, do you see how you get that? Yes? No? Yes? Okay, good, thank you. I mean, if you don't want to say yes, you can parry the platyp. It's always difficult to tell what Perry means when he says that, but in any case, yeah, those are different. Those are the same molecule. Those are not stereoisomers of each other. They are the same. So you have to get used to moving molecules around, rotating around bonds, twisting around, flipping things over to try to see whether they're the same thing or not. I'll say more about that in a little bit. Okay, are there any questions about these definitions? So let's talk more about enantiomers. As I said, enantiomers are stereoisomers that are mirror images of each other. Okay? So, because they're stereoisomers, they are not the same thing. But they are nevertheless mirror images of each other. And enantiomers always have a property. If a molecule has an enantiomer, that is, if it's not the same thing as its mirror image, then the molecule is said to be chiral. So the property is chirality. And you can use the term chiral as an adjective to describe a molecule that is not the same as its mirror image. So enantiomers, because they are not the same as each other, they are chiral molecules. So chirality is a property that's intrinsic to the world around you because you are made of chiral molecules. And you can demonstrate this in a couple of ways. One is to look at your hands. You have your right hand and your left hand, and they are mirror images of each other. Sometime as a child, you were playing with your hands and you were like, those are just, they look the same, but I can't slide one to the other and have all of the fingers and the thumbs and the palms and the back of the hand in the right place, okay? Different. The second place you have this experience is looking in the mirror and or watching yourself during a Zoom call or on the phone. Now, if you take a selfie of yourself, that's redundant, I'm sorry. Sometimes, depending on how you have your settings on your phone, you'll see a mirror image of yourself instead of the actual version of yourself. Have you ever looked at yourself in the mirror and then looked at a picture of yourself and thought, those are not the same person, right? And then you realize to your horror that the person that's in the picture is actually what everybody else sees. And the person in the mirror is, only you see that, right? That's an example. You are chiral, so you are not the same as your mirror image. And we all have to figure that out and adjust to it. So this is a fundamental property of molecules, and let's demonstrate it. So this is easiest to demonstrate with a model set, so you may want to spend some time with a model set, but I'm going to draw. You need to get good at drawing molecules to determine whether they're mirror images of each other, and then convincing yourself that they're not the same. So here is a molecule that is chiral. It's going to be a simple molecule where the carbon in the middle is attached to 4 different things. I'm not sure this is a real molecule. I don't know how stable it is. We're going to use a dotted black line to be a mirror. And then we're going to go through the looking glass to the other side of the mirror. And whatever we draw on the right must be a reflection of what's on the left. So for example, here is the carbon, here is the hydrogen, but whereas the fluorine on this side of the mirror was pointing as a wedge towards the right, the fluorine on the other side of the mirror must be a wedge pointing towards the left. Do you see how that's a reflection? Yeah. Similarly, the bromine should be pointing towards the left. The chlorine, which used to be pointing towards the left and was a straight line, will now be pointing towards the right. Okay? Those are 2 mirror images of each other. It may help you in the early stages to highlight in different colors the various portions of this molecule. All right? Those are mirror images of each other. Now, we need to convince ourselves that they are, in fact, not the same thing. So there's multiple ways to do this, but let me suggest that you develop a tool of molecule move inators that will help you move molecules around on a page in a way that's consistent with their 3D shape. I already showed you the pancake flip inator. This is going to be the molecular, now I'm going to show you the molecular claw inator. So the claw inator is from Toy Story, where Woody's in the machine and he asks the aliens who's in charge here, and they all say, claw, right? The claw reaches down and grabs on the hydrogen, and then it twists the molecule around 180 degrees. Okay? So spin that molecule around 180 degrees, and then let's redraw it after the claw inator has done the operation. Now the chloro is going to be pointing back to the left, and the hydrogen is still going to be up. So the reason I'm doing the claw innator is because I want to see if I can line up the hydrogen and the chlorine as they are over here. What should happen here? If I spin this around 180 degrees, where is my bromine now? It should be a wedge, right? And it should be pointing towards the right. And the fluoro should be a dash pointing to the left. Sorry. Okay, great. So now I'm going to slide this over and compare. And do you see the problem? I can get hydrogen and chlorine to line up, but I can't get fluorine and bromine to line up. And then you say, all right, Chuckles. That's occasionally when I'm frustrated while driving, I call other drivers Chuckles. Chuckles over here doesn't know how to use his directional. So now we're going to expand the claw. We're going to hold on. We're going to grab either side of the bromine and the fluorine, and we're going to exchange their places 180 degrees. Okay? So when we do that, that ought to trade the places of the hydrogen and the chlorine. And it should also trade the places of the fluorine and the bromine. Can you imagine what we did there? So now fluorine's back in the right spot and bromine's back in the right spot, but chlorine and hydrogen are not. And so we could continue this process of flipping things over again and again. Worlds without end, those are not the same thing. Yes?
Do you have to do the second claw function to understand compare?
No, you don't have to do the second claw function to understand. I was just like, I don't know what I was doing. I mean, it's great if it was obvious to you that they were not different after the first claw innator, but this was to satisfy the rest of anyone out there who continued to doubt. You can continue to flip it around, and it's just not the same thing. Okay? All right. Now, molecules that are not the same as their mirror images are chiral, as I said, and have an enantiomer. So, this molecule is chiral, this molecule is chiral, and the relationship between the two is they are enantiomers. Let's be really specific here. Some people sometimes get confused. Enantiomer is a relationship word. It makes no sense to ask, is this an enantiomer? It's like asking you, as I've said before, are you a cousin? Of whom, right? That's the question that is begged by that term. An enantiomer is a relationship word. That's a relationship between two molecules. They are enantiomers. But chirality is a property of an individual molecule. So the enantiomer on the left is chiral, and the enantiomer on the right is chiral. Okay? One important, go ahead.
Is the easiest way to draw the enantiomer just to flip what's dashed and what's wedged, or is that going to be this wrong?
Great, we're getting there, and that will work, but be careful. That will work, but I need to disclose my evil tricks to you. So you mentioned flipping dashes and wedges, and I want to say something about that. One of the ways you can generate chirality is for your molecule to have, the fundamental definition of chirality is that the molecule has to be not the same as its mirror image. But one of the ways that you can be chiral is to have what we're going to call a stereocenter. And I'm going to highlight in pink the stereocenter. A stereocenter is an sp3 hybridized carbon attached to 4 different things. The actual definition is a little bit more broad than that, but for now, that's going to be okay. An sp3 hybridized carbon attached to 4 different things is a stereocenter. So one of the things you're going to need to be able to do is to look at a molecule and ask, where are the stereocenters? Okay? If a molecule has one stereocenter, it must be chiral. Okay? So one stereocenter, molecule is chiral. 2 stereocenters or more, who knows, might be chiral, but be careful. Let me give you an example of a molecule that might be chiral or not, depending on its 2 stereocenters, but be careful. Here's the molecule that we saw before. Let's look at carbon 1 and carbon 2. Is carbon 1 a stereocenter? Now remember, 4 different things, different, we're going to use the same exact standards we used for E and Z. In other words, if you can't find a difference all the way out, then they're the same thing. This methyl group is different from this tertiary carbon, which is different from this secondary carbon. So yes, I would say that is a stereocenter, right? How about carbon 2? Is that a stereocenter? You bet. Now, is it chiral? Let's draw the mirror image. Now we're going to use our molecular claw innator. We're going to grab the molecule right here. The claw is coming down from above, and we're going to spin it around 180 degrees. Gasp. It's the same thing. If a molecule is the same as its mirror image, then the molecule by definition is not chiral. A molecule that has stereocenters but is not chiral, we call a meso compound. And I'm not sure where that comes from, but meso compounds are the worst because I can draw them in ways that makes you think they are stereoisomers and they're enantiomers, and yet they are the same compound. I will disclose those evil tricks next time. See you on Wednesday.